Consider a metallic wire at rest in the laboratory. The wire is passed through by a current I, directed to the left. In a simplified but very effective model of electric current in metal, what actually move are some free electrons in the wire. These electrons are called conduction electrons and move to the right with a velocity that with ordinary electric currents is very small, of the order of tenths of millimeters per second. The positive charges are the nuclei of the metal atoms and are stationary. The current generates a magnetic field like in the drawing. According to the electrical current model and laboratory experience, the current carrying wire is neutral, and if we place a stationary test charge next to it, the charge does not feel any force. If, instead, the test charge moves, for instance to the right with a velocity v, the charge gets attracted by the wire with a magnetic force that is known as Lorentz force. In the 1960s, Nobel laureate Edward Mills Purcell provided a basic mechanical explanation of this phenomenon. The magnetic force, felt by the test charge moving parallel to a fixed current carrying wire, is, in fact, an electrostatic force when observed in the rest frame of the test charge. In the rest frame of the test charge, the positive charges of the wire are seen as moving, and, then, their density is modified by Lorentz length contraction differently than the density of the moving electrons. Therefore, the wire becomes positively charged, and the stationary test charge is attracted by it. If you do the calculation, that electrostatic force has exactly the same magnitude as the magnetic force measured in the lab frame. This explanation is considered one of the most astonishing successes of special relativity. The calculations fit perfectly with the Lorentz force law. Moreover, think about it, all this seems to be one of the few relativity consequences showing up in everyday life. On YouTube, you can find many well-made videos on Purcell's explanation of magnetic forces. For a far from complete list at the moment of this video, please check the links in the description. But does length contraction really explain magnetic forces? I will show you there are at least 3 problems with that explanation. Let's get into them. Problem number 1, Ampere's force law. Purcell's approach is impressive in exactly explaining the magnetic force on a single test charge, but what about the magnetic force between 2 current-carrying wires? For example, according to Ampere's force law, 2 parallel wires, passed through by currents in the same direction, attract one another. With Purcell's explanation, however, it should happen exactly the contrary. Consider what sees an observer at rest in the same reference frame of the conduction electrons. In the reference frame of the moving electrons, both wires become positively charged, and then they should repel each other. The same inconsistency appears with wires passed through by currents in opposite directions. Therefore, Purcell's approach alone cannot explain magnetic forces. Problem number 2, the principle of relativity. Both laboratory and test charge frames are inertial frames. Therefore, the same laws of physics apply to them. That is the relativity principle. However, Purcell's explanation seems to violate that principle. In the lab frame, the conduction electrons move. Therefore, their mutual distance should contract, and their density should be higher than that of the positive stationary charges. But the wire is neutral. How is this possible? It is possible because the conduction electrons feel a mutual repulsion and rearrange themselves to restore a zero net charge, more or less according to the same principle by which negative charges, separated from the positive ones over a metallic surface, move to cancel out the overall electric potential difference. Therefore, why do electrons not do the same in the reference frame of the test charge? Even from that inertial reference frame, the electrons should rearrange to compensate for a higher positive charge density and to restore a zero net charge. I see in all that a lack of reciprocity, the same reciprocity demanded by the principle of relativity. Problem number 3, the superconducting ring. Imagine a superconducting ring in which a direct current I circulates clockwise. The conducting electrons move counterclockwise at a velocity v. I have chosen a superconducting ring simply because the current keeps flowing without a battery. In the reference frame of the laboratory, the ring is neutral, as usual. If we now consider a bunch of negative charges moving around the ring, counterclockwise at the same speed as the conduction electrons, according to Purcell's explanation, these charges are electrostatically attracted by the ring. In other words, according to these charges, the ring is overall positively charged. However, this is not possible. The total charge of a body cannot change simply by changing the frame from which we observe the body. In conclusion, what appeared to be an astonishing success of special relativity taking place in an everyday phenomenon risks becoming relativity's Achilles heel. For instance, the superconducting ring experiment tells us that relativistic length contraction cannot be a real phenomenon because it is at odds with the basic principle of total charge conservation in isolated systems. If you want to go more into detail, please check the links to my publications in the description. Thank you.